So good afternoon. In today's video, we will be discussing the case study on PID controllers. In our previous video, we discussed what is a controller, what is the role of a controller. Now here, we'll be discussing a case now where the PID controllers are applied, how the response of the system is behaving. So just to recall, now a controller is a device introduced in the system to modify the error signal and to produce a control signal. So you can see we have a controller. Now this controller, it acts on the error signal which is generated by the error detector, and the controller, it produces a signal, that is the actuating signal, to modify the system parameters, and therefore the desired output is reached. So the controller also modifies the transient response of the system. So there are various type of controllers what we have already discussed. So the proportional controller, the integral controller, and the proportional, integral and derivative controller, what we call it as the PID controller. So now this, it is the PID controller. Now the PID controller, what it does is it produces an output now which is the combination of the output of the proportional, integral and the derivative controllers. So it produces what we call it as the output, that is the output of the controller U of S. Now it is proportional to the input, it is proportional to the integral of the input, and it is proportional to the derivative of the input. So that is what we have written over here. It is Kp into E of t, that is nothing but the proportional controller, and then we have the integral controller, and then the final one we have it as the derivative controller. So what the PID controller does is it uses the advantages of all three controllers. So it is a combination of all three controllers. Now when we apply Laplace transform, now this it is the required transfer function, now where Kp is the proportional controller gain, Ki is the integral controller gain, and Kd is the derivative controller gain. So your proportional, that is your PID controller, now it is used to improve the stability of the system and also to decrease the steady state error. So this is the main advantage of your PID controller. So in today's video, we will be discussing a case. Now what happens if this controller is there, how the response is getting modified. Now I can see based on the time domain specifications, your PID controller, now your proportional controller, it decreases the rise time, whereas it increases the overshoot, that's the peak overshoot, and there is a small change in the settling time, but the steady state error is decreased. So when you introduce the proportional controller, it almost decreases the steady state error. And similarly, if you introduce an integral controller, now your steady state error is almost eliminated. So that is the main advantage of your integral controller, now where it eliminates the steady state error, whereas it decreases the rise time, but the introduction of your integral controller, it increases the overshoot, and also the settling time also increases. And finally the derivative controller, now I can see there is a small change with respect to your rise time as well as your steady state error, whereas this integral derivative controller, now you can see it decreases the overshoot. So it acts on the system ahead of whatever it occurs. Therefore it is with respect to time domain. Okay, it is the derivative of your system. So therefore it acts, it anticipates the error and then it acts on it accordingly. Therefore the peak overshoot is decreased, and also your steady state output time, that is the steady settling time, is also decreased. So in PID controller, now we are going to use the advantage of all three gains: the proportional gain, the integral gain, and the derivative gain. So as I told you, we will just consider a small system, a mechanical system, now where we have a mass M, a spring and a dashpot. So F is nothing but the applied force to the system, and we have X is nothing but the displacement of the system. Excuse me. So now when we just apply the transfer function, when we just model the system, this is the transfer function of the mechanical system, where M is the mass, B is the friction coefficient, and viscous coefficient, and K is the spring constant. Now consider a case now where we have mass is equal to 1 kg, and then we have your viscous coefficient B, which is given by 10 Newton second per meter, and then the spring constant K, it is 20 Newton per meter, and your force, applied force, is 1 Newton. So therefore this is the case what we are going to consider. Now this, it is a mechanical system, and when you just substitute all these values, now this is the transfer function, modified transfer function, what we are going to consider as a case. Now for this system, in order to improve the performance of the system in terms of time domain specification, now what is the role of your PID control? So that is what we are going to discuss as a case. Now you can see I've just used the MATLAB in order to find the response of the system. So we have just taken the open loop response, that is open loop step response. So the input is a step system. There is a small coding made with respect to the previous, that is the transfer function. And now you can see, now this is the numerator and this is the denominator. Now we are just going to find the step response with respect to numerator and denominator, and this, it is the step response. Now where you can see the response of the mechanical system, now the rise time is very high. Now rise time, it is 90% of the final value. Here the final value for us 0.05, that's the final value. Now it is almost 90%. So you can see now rise time is more than 1 second. Our rise time, it is more than 1 second for us. So this is our rise time TR. But we don't have any overshoot, and also the settling time, you can see it takes more than 2 seconds. So where now you can see the system, it is a very sluggish system, and therefore its performance has to be improved. Now for which now we introduce the PID controller. So instead of directly applying the PID controller, first we'll apply what is a proportional controller, then your PI controller, finally the PID controller. So first is your proportional controller. Now you can see we have considered the proportional gain to be Kp is equal to 300. We have assumed, and this is after various trial and error method. And without trial and error method, there are numerous tuning methods which is applicable in order to find this gain value. But here we have just assumed. Now for which now the transfer function is developed, and your response for a step input is being taken, and now this indicates your response. Now you can see the rise time is reduced less than 0.2 seconds. Now whereas in the previous case it was more than 1 second, but here it is 0.2 second. And also your settling time, it is less than 1 second, but whereas here it is almost 2 seconds. Sorry, it is almost 2 seconds, but whereas here it is less than 1 second. So therefore now you can see the rise time has improved, the settling time is improved, but the introduction of a proportional controller has the overshoot in the system. So it has made the system, we have overshoots in the system. So this is another disadvantage. Now we have already seen in the tabulation in the previous case. So it introduces peak overshoot. So how to eliminate this peak overshoot? Now that's the next one. We combine both proportional integral controller. So that is your PI controller. Now here again 2 values we assume after various trial and error method, and then we find the response of the system. Now you can see the response of the system. There is a small overshoot in the system still existing. Your rise time is improved, and also your settling time is improved. There is a small overshoot in the system. Now finally we are just going to use your PID controller. Now in your PID controller, now all these 3 values it is got after several trial and error method. Now as I told you, there are various tuning methods available which we can use it, but here it is done on trial and error method. And the transfer function, already we have found what is the transfer function of a PID controller in our previous slide. So we apply the transfer function, we find the response. Now you can see this is the response. The overshoot is almost eliminated. There is no steady state error. The rise time is also reduced. So this, it is a perfect response of the mechanical system. That is, the response of the system is improved by the introduction of a PID controller. So therefore this system is a very fast system without any error. So the sluggish system, with the introduction of a PID controller, now the system response have improved. So that's the advantage of a PID controller. which we have seen in terms of a case. So this coding is being done in MATLAB, so for further references. So thank you very much. Thank you for your patient hearing. Thank you.